we have a floor plate here. I have laid out the axis, it just to sort of uh, um, horizontal and vertical lines to just to point out my center of rigidity is here. And you can sort of see that I have a small dashed line behind it, and this is where I'm going to show you what happens when the floor plate has a torsion. The torsion, remember 1170.5, we have to do a compulsory 10% eccentricity, that is accidental. So imagine our earthquake force is heading this way, that is 100% is heading this way, north and south direction. And also we are allowing for, say, okay, I've got a 10% eccentricity that is going hitting my floor plate, causing my floor plate to twisting back and forth. So in this case, we're going to use a small angle theory to work out what are the deformations of the walls and to what angle, and therefore we can work out the induced force. Okay, I'm going to do an example here. Suppose my floor plate, okay, is going to twist to a certain angle. I'm going to say my floor is back and forth, and I can say twist the floor angle here. And you can see this is um, the axis after my floor plate is twisted. I'm going to say my maximum twist is here. And you can see in comparison to original axis, the red lines, it forms an angle to each walls, right? Let's move it to the center of it. So you can see that the wall 4 is supposed to be here is going to be moved. And the same to wall 1, 2, and 3. They're all moved to a certain angle. And this angle here, that is perpendicular to the wall, that is perpendicular to the wall, and we call them small angle theta. So they're all theta. That is the small angle because the angle is so small, and we will be when we're calculating it, we just use the small angle theta. Um, I'll talk about that in a minute. So what about the deformation, you're wondering? So the deformation is here because this is the horizontal and this is the base, right? It's going to move the walls move from here, that was supposed to be here, and move to here. And it moved to an angle, but at a certain distance. So over here, we call it this deformation is delta. And here, deformation delta, or displacement delta, here, delta. So as you can see, the further away from the center of rigidity, the angles are the same. But however, the deformations are not necessarily the same. If you have a close one, say wall 4, that is relatively close to the center of rigidity compared to wall 1, and the deformation occurred at a wall 4 is smaller than deformation on wall 1. So you can see that from Hooke's law, it explains that wall 1 is going to have a larger shear force, induced force than wall 4 because the deformation is larger, but the theta angle is the same. So from the Hooke's law, we have the force is equals to the stiffness times the deformation. All right. So the stiffness, as I explained in the previous video, when we're working at the center of mass and the center of rigidity, the stiffness for the frame, for the wall frames, is essentially the length of squared the stiffness. So basically, so the force, so the Hooke's law, the force is equals to K, that is L squared. We call it L squared, and times our theta. And the next, we need to figure out what is the theta. So because we're using the small angle theory, essentially the angles are small. as I said before. So to work out the theta value here, deformation here, is usually to be sine theta times the perpendicular distance here, which is di in the visual one, and for wall 3, and that is the di, right? Let's call it d3, and let's call it d2, because this is the individual, and this for wall 2, the distance is d2. It's perpendicular to the wall, and for wall 1, it's perpendicular to the wall 1, and here is d1. So the theta value is just essentially the theta times your perpendicular distance, d. So I got my theta as theta times my di in the visual distance. So we can see from the equation here, the L squared is given as essentially the length of the wall, and the di is given. So those two quantities are given. So our force, we can say, just rearrange it, we can say is k theta times L squared times your individual distance. And that is the small angle theory we're using to calculate. That is the F is essentially the induced the shear force onto the wall, and that is the force. F force is causing these walls to move at a certain angle and resulting in a certain deformation theta. I said it again. That's the force induced causing these walls to move to a certain angle to a certain deformation theta, delta. Okay, now next, and we're going to work out, because we've already got the force, and we from the moment, uh, because it's going to creating a moment each force with respect to the lever arm, right? The d individual distance d is essentially the lever arm of the force. So the force times your lever arm get you the moment. We're going to call it a resisting moment. That is times your F times your D individual distance. And your F induced force is equation is already been calculated from Hooke's law. So what we need to do is just to substitute this equation down here. So we got our moment, individual moment resisting on each wall, and that is essentially to be, when you substitute it in, you got your k theta times L squared, and you got 2di, so it's going to di squared, and that is your resisting moment for each wall, for each individual wall. Okay, so we've got 4 walls, and we need to work out what is the k theta. We don't need necessarily to know what k theta is in a moment, but eventually we can calculate them together. So how do we do that? So this resisting moment, the resisting moment of the wall is because the wall is resisting what? It's resisting this 10% eccentricity torsion, right? The 10% eccentricity torsion, let's call it Tm. You can work it out by equivalent static method, and by doing torsion analysis, you get your torsion moment. I'm going to make a number here, say 100 kilonewtons meters. That's your torsion moment. That's your induced by your 10% torsion. So I've got a torsion moment here, and we need to know what these walls are taking because of this torsion, and we work out this from Hooke's law, and we work out the induced force, that is k theta times L squared times the distance of the perpendicular to the wall, and work out, and then we got this moment here, resisting moment, that is in relation to my induced force times my lever arm di. And then I got my torsion moment here. That's the total torsion moment. And then what's my total resisting moment? I've only got an individual moment here. So in this case, we just work out each one of the wall's resisting moment here. Let's say wall 4. So we have our mr4 that is equal to k theta times L squared. That L is 4, L4 squared. Let's call it a D. There's a DI 4 here. There's a D4 squared. So this is my wall 4 resisting moment. Similarly, we can get my wall 1. So my wall 1 resisting moment is k theta times L1 squared times D1 squared. Same thing, we do L wall 2, so mr2 equals k theta times L2 squared times D2 squared. And we've got wall 3, last one. So mr3 equals k theta times L3 squared times D3 squared. Okay, so we've got all the resisting moment combined together to resisting the total torsion moment. We can write equation here. We can write this below. So we have resisting moment summation of all of them plus resisting moment 2 plus resisting moment 3 plus resisting moment 4. That is equal to my total torsion moment, which is 100 kilonewton meter. And the only thing we don't know is k theta. Once you combine them, and we can work out your k theta is eventually a number. You can work that out. You can work out a number here. And then let's make up a number here, say 20. And then what we need to do, so the things gets clearer now, because we've already worked out the induced force, right? Due to its stiffness and its distance. This is using the small angle theory, right? This is what we already know. So what we need to do is we substitute whatever the k theta is, because the k theta is all the same through all the walls, right? Because the theta angle is the same. It's the same for all the walls. And then what we need to work out is we just need to substitute 20 back to here, k theta, and then you will obtain this Fi value for each wall. So this is how we're using small angle theory to calculate each wall's induced shear force. That shear force comes from the 10% eccentricity, because of the eccentricity causing a little bit twisting moment that is circling around all the walls, and we need to find out what forces is induced to each wall, and that's why we're using this small angle theory based on Hooke's law. And once we work out what is the k theta, and we can substitute the k theta value back into the Hooke's law, and we will find our individual forces for each wall. Alright, so yeah, this is the small angle theory. I'm hoping this is clear, and if you have any questions, make a comment below, and thanks for watching.